So let's talk about reaction mechanisms. We were just talking about collisions. Most reactions actually occur in more than one step. When we write a chemical equation, regular molecular equation for a reaction, we show the substances that are present at the beginning, the reactants, and we show the final products, but we don't show the details of what happened in the middle. Okay, there could be an awful lot of stuff that happens before you get to this. So the reaction mechanism is a series of individual chemical steps by which the overall reaction occurs. So each of those steps, called an elementary step, represents the exact species that are colliding in the reaction. So, yeah, I don't have anything to add to that. Sorry. So if we look at this reaction of hydrogen and iodine monochloride, the mechanism for this reaction is that it occurs in two steps. So a hydrogen molecule collides with an iodine monochloride molecule, and that generates hydrogen iodide and hydrogen chloride. The hydrogen iodide will collide with another iodine chloride and produce hydrogen chloride and iodine. So there's two steps in here. We can't see that or predict that from the overall chemical reaction. The individual steps here have to add up to the overall reaction. So let's just double check and show that they do. You should have done this in 1A where you added chemical equations. So what's happening here is that this HI that's formed gets used up in the next step. And so we could say it cancels out, right? We've got an HI on each side, and so this is made and it's used up, so we can cross those off. And we'll look and see if there's anything else that does that, and there's not. So we've got H2 in the gas state and 2 ICLs. And that's going to form 2 HCl's plus I2. So when we have mechanisms, the individual steps have to add up to the overall equation. So this is an intermediate. A reaction intermediate is a substance that's formed in one step and then consumed in another. So you don't see it as a reactant, you don't see it as a product, but it is there in the middle of the reaction. So the reaction mechanism gives us this nice detailed description of what's happening on the molecular level. It shows us what are the species that are colliding, the individual collisions that must occur. The kinetics help us to determine the mechanism of a reaction. So we can measure the kinetics of the overall reaction and then work backwards to find a mechanism that's consistent with the kinetics. And anybody wondering why the heck anybody wants to do this? Yeah? Well, if we've got a process, say an industrial process, and we want it to be more efficient, if we understand at the molecular level how the process is occurring, then we can tweak conditions and make it happen in a way that's more positive for us. You could make it maybe happen faster or more completely, or maybe there's something that you want to prevent from happening. So there's a lot of practical reasons why you might do this. And then there's also a group of people that just do this for the sake of determining mechanisms of random reactions. I don't know about them, but this is an aspect of chemistry. Okay, so the elementary steps are characterized by how many particles are involved in the step. It's called the molecularity. We just make up these words, don't we? So a unimolecular step is one that involves one molecule. Maybe it breaks apart, something happens, it does it all by itself. One molecule. Bimolecular, you have two things. Now, they can be the same substance. You could have two atoms of the same element colliding and forming a product. That's still bimolecular. Or you could have two different substances colliding and forming products. Okay? You can also have termolecular, which would be three different particles colliding. They have to collide simultaneously with the correct orientation. Those sorts of elementary steps are very rare. They do exist, but they're very rare. Any questions? So unimolecular, one molecule. Bimolecular, two molecules. So the elementary steps can be deduced from their rate laws, from the rate law. But you can't just deduce it from the overall reaction, but you can get the individual rates. The individual steps. I'm blithering, sorry. The molecularity is going to equal the overall order of the reaction. So let's just look at these examples. Here we have a rate law where the rate is equal to the rate constant times the concentration of A. This rate depends only on the concentration of A. For that, we can predict that the elementary step corresponding to that is unimolecular. It just is A forming products. So the rate depends on the concentration of A. Here we have a second order equation where the rate depends on the square of the concentration of A. That's going to happen when we have a bimolecular step where A is reacting with A. They have to collide. So the molecularity here of 2 corresponds to the overall order of the rate law. This has an order of 2, this has an order of 1. Here we've got a rate where we've got A times B. So this is a second order reaction overall, right? Because you add the exponents. And so this should also have a bimolecular elementary step. Here we've got A and B colliding. If you had the rate is proportional to A cubed, that would mean that you have a termolecular reaction where you have to have 3 A's colliding. Very rare. Here we've got A squared times B. That would be 2 molecules of A and 1 of B. Here we've got A times B times C. So we need 1 of each of those colliding. So when we look at the rate law, we can work backwards and find a mechanism step, the elementary step that would correspond to that. Any questions? So usually one of those elementary steps is much slower than the others, and we call that the rate determining step, because that's the holdup. It's the thing that limits the overall rate of reaction. If you got rid of that or you altered it somehow, you could speed up the whole process. So it's a little bit like a traffic situation like here, where you've got them, they're working on the road and they've got this lane closed off, right? So we end up with this bottleneck here where people are merging into one lane. This is the holdup for traffic to flow, right? If we cleared that out, then traffic could go faster. But this is what's limiting the rate of travel. Does that make sense? So there's typically one elementary step that is a lot slower than the others, and that's the one that's going to primarily affect the overall rate. So let's look at an example. Here we've got NO2 plus CO forming NO plus CO2. So the rate law is this. K is K times NO2 squared. This is not something that we can get by looking at the equation. It's determined experimentally where you measure the rate of the initial rate at different concentrations. We did that at the beginning of this chapter, right? So this would be told to you in a problem like this. So could this be a single step reaction? This rate law is implying that we have an elementary step where you've got NO2 plus NO2 forming some product. Okay, the computer caught up with me. So this rate law, being second order in N2, means that there's a step that's bimolecular where we have N2 colliding with NO2. Sorry, not N2. NO2 colliding with NO2. Well, do we see that anywhere in the overall reaction? We just see one NO2, and then there's CO in here also. So this cannot be a single step reaction. There's got to be something else going on. This reaction between NO2 and NO2, because that shows up in the rate law, that's probably the rate determining step. So a possible mechanism would be here, where we've got NO2 plus NO2, and we get that from looking at the rate law. We think, well, what could happen when those two run into each other? Well, this is one of the products, NO. So if those collide, we could get a transfer of oxygen from one to the other. And then this one could collide with CO, and we could end up with this, right? So when we add these two steps, do we get the overall equation? Well, let's just do it and find out. So I've got an NO3 over here and an NO3 over there. It gets made and it gets used up. And I've got an NO2 here, and I've got two of them up there. So one of them is getting made and used up again. So I end up with NO2 plus CO. That's not a C. NO2 plus CO. Oh, there. NO plus CO2. So adding two chemical equations is like adding two math equations, where you're adding on both sides. So if you have an X on one side and an X on the other side, they go away, right? And so we can do that here as well. When we add these two mechanisms together, we get the same overall reaction. So this is a possible mechanism. Any questions? Yes?
It's the bottom one. Oh, never mind. It's on step 2, really. Is it the bottom one step 2?
Yeah, well, this would be step 2. Yeah, and we could tell that this is step 2 because NO3 is involved in this reaction and it's not actually present initially. So that couldn't happen first. This one would have to happen
I was
first.
thinking that if the bottom one is like step 2, then why do you cross out the NO2s if that one's not used up because it's second in the product?
That's an excellent question. So if this is the second part and I've regenerated NO2, why did I cross these out? Well, if I don't, let's see what happens if I don't. I end up with 2 NO2 plus CO, forming NO2 plus NO plus CO2. So this reaction, as we've written it here, is using 2 moles of NO2, but then it's also producing 1 mole of NO2. So the net result is it only used 1. Does that help?
Yeah.
Any other questions? So in that possible mechanism, the first step was slower. That means that the first step has a higher activation energy, because a higher activation energy would give us a smaller rate constant. We can't compare temperature here because This is one reaction, it's all happening at the same temperature. But the rate constant depends on the activation energy. So we can draw an energy diagram for this, where we've got energy increasing on the y-axis, reaction progress on the x-axis. We're starting here with our reactants, and in order to get to an intermediate, here's our transition state, and then we're going to get to the end of step 1 here, and we've got to get up and over this hump. And then the second step is also going to have an activation energy. Everything has some sort of an activation energy, and so we have to get up over that hill and then down. Overall, this is an exothermic reaction, and so the products are lower in energy than the reactants are. This activation energy for the first step of the reaction is larger. This activation energy is smaller. How do we know that? Well, we looked at the rate law, and the rate law corresponded to the first step. That told us the first step was the slow step. The slow step has the higher activation energy. The faster steps have lower activation energies. You can kind of think of this as a roller coaster. And so if you manage to get up to the top here, then as you coming down here, you're going to have enough energy to go up and over and finish off the course. But this is the hurdle. This is the high point where we have to have enough energy to get up there. Once you get up there, it literally is all downhill from there. Energy diagrams are helpful because it's the closest thing we can have to a picture of what's going on. And so it's very rare for us to have any sort of a scale here, either on either axis. We're just getting an overall picture. Which one's higher, which one's lower, the product's higher in energy or lower, etc. So here the first step determines the overall rate, and that first step predicts the same rate law as the experimental data. Any questions?